Welcome to this video all about the concept of moles in chemistry and how to do molar calculations. This is part of the Step Up to ChemHE program. It's a series of video workshops designed to help the transition of foundation and first year students into chemistry focused modules who don't have a strong previous background in chemical sciences. You'll need around 20 to 30 minutes to complete this video workshop. There are a number of quick practice questions throughout, and at these points you can pause the workshop and work through the questions at your own pace. There's a full set of practice questions to attempt on a separate sheet at the end of the workshop. Now, to get the most out of this session, you'll need a periodic table such as the one you can download off the Step Up to ChemHE SharePoint homepage, and a calculator or access to Microsoft Excel. So our learning objectives are to become familiar with the key terms highlighted. We'll go through the important relationships between mass, molar mass and moles themselves, as well as some simple conversions between these units of the type that you might be assessed on in your chemistry focused modules. We'll then look at the terminology required when it comes to dissolving chemicals in solvents and calculating concentrations and molarities. By the end of the video, you'll be able to see your learning in context by recognizing real-world examples of why this content is so important. Now, in this video, there are some assumptions made of basic maths competency. So, for example, I expect users to be able to know and recognize that, for example, 1 gram is equal to 1000 milligrams, or 1 litre is equivalent to 1000 millilitres. If this kind of conversion is new to you or challenging for you, then what you need to do is stop watching right now and book an appointment as soon as possible with one of the academic skills maths tutors, because that will give you the foundational knowledge required to engage with your science degree. Chemistry, as this slide tries to show, is really based on maths. If you can't do maths, you can't do chemistry, and the maths understanding has to come first, especially with this content that I'm about to go through. So, the concept of the mole is very fundamental throughout all of chemistry, and something that people who have to learn chemistry relearn it in higher education rather, without the grounding in lower education, can have real difficulty with. It requires a very basic shift in how you think about combining matter. In chemistry related problems, you simply can't treat chemical reactions the same way as we're used to thinking about combining and mixing things in everyday life. So for example, let's imagine you're going to make a cake. Most people like cake. So the recipe will tell you to mix, say, 500 grams of butter with 500 grams of sugar. If you do that, then you'll get part of a cake mix that weighs 1000 grams. So applying that concept to a chemical reaction, you might think that if you've got a ton of sodium, a ton of chlorine, if you react those quantities together, what you might end up with is 2 tons of sodium chloride salt. Of course, this is categorically not the case. If you look at any periodic table, such as the one you can download from our homepage, you'll notice, of course, that the atoms of the different elements have different masses. A single chlorine atom is heavier than a single sodium atom. For this reason, of course, if you react together, or try to react together, 1 ton of sodium and 1 ton of chlorine, there will be rather more sodium atoms in the reaction mix, so the reaction will not work as you expect it to. So, of course, what you need to do if you want to make, say, 2 tons of sodium chloride and not have any waste chemicals left over, is take however many billions of sodium atoms you'd need and then react those with exactly the same number of chlorine atoms. It's a 1-to-1 reaction. If you want to do it without any wastage, that is the way to do it. Of course, though, it would be completely impractical in the real world to say, alright, let's measure out 5 billion sodium atoms. We need to do something to allow us to work in units that are practical and relatable to real world problems. And this leads us to the use of the mole. It's very important to demystify this term for people new to chemistry. A mole is just a number, just a very, very big number. To be precise, it is 6.02 times 10 to the power of 23. What that means is that in 1 mole of a pure chemical substance, and that could be any substance, could be sodium atoms, chlorine atoms, water molecules, gold metal atoms, a certain amino acid, a certain protein, any pure chemical, in 1 mole of that chemical there are going to be 6.02 times 10 to the 23 units, shall we say. So atoms, ions, molecules or biomolecules present. This number is called Avogadro's number, and it's commonly abbreviated with a capital N and a subscript capital A, like we see on the slide. The reason why we work in moles rather than atoms, ions, molecules or biomolecules is just convenience. How much easier and simpler is it to write a mole of water rather than 6.02 times 10 to the power of 23 water molecules? So you'll probably have worked out by now that there's a relationship between the number of moles of a substance in a sample, the atomic or molecular mass of the substance in the sample in question, and the actual physical mass of the sample, what we can reliably weigh. This relationship is one of the most important things to understand when learning chemistry. So the relationship is this: the number of moles is equal to the mass of the sample divided by the atomic or molecular mass of the chemical in the sample. Likewise, with a simple rearrangement of the equation, the mass is equal to the number of moles multiplied by the atomic or molecular mass. Now, depending on your background, you may have heard the term atomic or molecular mass called slightly different things. When I went back to university, I learnt it as RAM or RMM, standing for relative atomic mass or relative molecular mass. Other people I met called it MR, capital M and a subscript R, meaning molar ratio. And a lot of people just called it molar mass, which seems to be the most common term in this day and age. They all mean the same thing. It's the relative mass of each atom or each molecule of the chemical in the sample. I'm going to call it molar mass throughout the rest of this video. The molar mass of an element is exactly the same as the mass number that you can find for that element in any periodic table. Now, units are important here. Going back to the top of the slide, the mole is itself a unit, and it's written like we see at the top of the slide, without the E, slightly abbreviated. The SI units of mass are kilograms, but it's much more common to see units of grams being used in the types of calculations that you're going to do. And then the common units of molar mass are grams per mole, or grams mole to the -1, as I've written on the slide. The molar mass of any chemical species can be worked out by using the periodic table. For an individual element, as I've said, it's just the mass number of that element according to the periodic table, as we see in the example at the top here. However, of course, the majority of chemicals that we deal with are not going to be pure elements. They're going to be molecules and compounds. So for these, all we have to do is look at the chemical formula of the species, or sometimes you have to work that out from other information. The chemical formula of the species that we're interested in, look at the numbers of each element that are present in that chemical formula, and then add up the mass numbers of those elements. For example, formic acid here is composed of a carbon atom, which has a molar mass of 12, 2 hydrogens, molar mass of 1, and 2 oxygens, molar mass of 16. In your discipline, you might be expected to work with slightly more precise numbers than the ones I've used here, but I'm just going to use whole numbers just for the sake of simplicity. So, bearing all that in mind, formic acid's molar mass is 46 grams per mole. Right, to make sure that you've got your head around these concepts so far, in the next slide, there are just some very simple problems and conversions for you to do. So you can pause and go through those now, and after the next slide I'll reveal the answers to all of those conversions on the subsequent slides. So once you're done with that, then carry on with the rest of the video. So here are the problems, and in a moment I'll move on to the answers. Here are the answers for the first 3 problems. And here are the answers for the last 3. So familiarize yourself with these and make sure that if you didn't get the practice problems all correct first time, make sure you understand where you went wrong before moving on in the video. Right, just to give one example of the usefulness of understanding relationships between moles and mass, we can think about chemical yields. These are extremely important in industry, so if you're making a certain drug, for example, by reacting a precursor with another chemical, you want that reaction to be as efficient as possible so that you spend less time purifying the final product, don't have to buy as much of the precursor, and can manufacture the drug generally as cheaply as possible. You can measure the mass of precursor that you put into the reaction, and likewise you can measure the mass of final product that comes out of the reaction. But of course that information doesn't tell you the yield. What you need to do is calculate the number of moles of precursor that you put in using its molecular mass, the formula we saw previously, and do the same thing for the final drug. Once you know the number of moles that went in and the number of moles that have come out, then you can do a very simple percentage calculation as we see here, and that gives you the correct yield and shows you the efficiency of the chemical reaction that you managed to achieve. So here is an example problem which you can go through and attempt to do just that. So you can pause the video now, have a go at it. In a few seconds time I'll bring up the correct solution on the slide. Okay, there we go, there's the solution. Again, if you didn't get that right, pause again at this point and satisfy yourself, understand where you went wrong in the calculation before moving on. Okay, once we've got our heads around the relationship between mass, molar mass and moles, we can then think about applying this concept to not just solid chemicals but chemicals in solution. Dissolving a chemical in an appropriate solvent, very often water, is one of the most convenient ways to transfer, mix and react precise amounts of different chemical species. That's why we learn to do it in the lab. So here we need to introduce some general terms which are of kind of key importance to the chemist. So we've got solute, a chemical usually initially in solid form that is added to a solvent and dissolved in it. An example would be salt. Solvent, a chemical in liquid form that dissolves the solute, usually water but not always, but I'm going to use water as an example. And solution, which is simply a solvent with some solute dissolved in it. An example would be salt water or brine. And now the term concentration. No, not that type of concentration. Now, this is a very general term. It simply means how much of a certain solute is present per unit of volume in a solution. There are many ways to express a concentration because, of course, there are many different units of mass and of volume. Some very common, some quite rarely used. The units that you'll commonly meet in chemistry will be grams per litre, milligrams per litre, and percentage weight over volume. Now, it's important to make a distinction here. The term molarity, on the other hand, means something very specific. So molarity is a type of concentration, but precisely it means the number of moles of solute present per litre of solution. The units of molarity can be written as moles per litre, moles, decimeters to the -3, or just molar, abbreviated to the capital M. They all mean the same thing. Which variation you commonly see depends on what is generally used in your discipline. An examiner is very unlikely to be unfair and interchange between those terms in the same assessment, so you're safe generally to learn and recognise the variation to express molarity that's used for your specific chemistry module, though it certainly doesn't hurt to be familiar with all of the different common ways of expressing molarity. Also common, especially in biochemistry, is millimolar. So a millimole is 1/1000th of a mole. It really does depend on what is the most convenient unit to use to talk about the sort of concentration ranges that you're dealing with. Now, just as you'll be expected to be able to convert between masses and moles, so too you'll need to be able to convert between concentrations and molarities. So for these examples, you can pause as I introduce each of them and try to work out the answer before I reveal the method. So the first one, if a suspension of ibuprofen has the concentration of 40 grams per litre and the molar mass of ibuprofen is 206 grams per mole, how do we work that one out? Well, we just need our trusty formula from the beginning of the workshop to work out that the molarity of the solution is 40 divided by 206, mass divided by molar mass, and that comes to 0.194 moles per litre. In this next example, so we're going the other way this time. We're going from a molarity to a mass concentration. So the molarity of glucose, which has a molar mass of 180 grams per mole, in a blood sample is 4 millimolar. So what is that glucose concentration in units of milligrams per litre? So again, it's back to the old formula. Just rearrange the equation to make mass the subject, and then number of moles times molar mass, which in this case is 4 times 180. That gives you 720 milligrams per litre. So originally the molarity is given in millimolar, so we can do that direct conversion to milligrams per litre. Things get a little more complicated when we have to deal with concentrations that are not expressed using litres as units of volume. Now, this is actually quite common in medical sciences. For example, it would be more common to see an ibuprofen suspension labelled as something like 50 milligrams per 5 ml, because 5 millilitres is the dose that the patient will be given at any one time. So pause and think, how would we calculate the molarity of that? This looks more complicated, but it isn't that much more complicated. So what you have to think is that if there are 50 milligrams in 5 millilitres, how many would there be in a litre? That's your starting point. So there are 1,000 millilitres in a litre. 1,000 divided by 5 gives you 200. So we have to multiply our 50 milligrams by 200, which brings us to 10,000 milligrams of ibuprofen per litre of suspension. Now that's a big number to deal with, so although we don't have to, we can now simplify by dividing that by 1,000 to express the concentration in grams per litre. So that makes it 10 grams per litre. That's the mass concentration. And now we've got the concentration in units of grams per litre, we can easily convert that to a molarity as before. So it's just 10 divided by 206, and the molarity comes out at 0.0485 moles per litre. One final aspect that we're going to cover in this video is the relationship between molarities or concentrations and dilutions. When you dilute a solution, you add more solvent to it, decreasing the number of solute particles that exist per volume unit. There are many reasons you might want to do this in science. For example, a patient in hospital might require a dosage of a certain number of moles of a drug intravenously per hour, but this has to be aligned with a sensible amount of fluid that you can put into a patient's body per hour. And so the concentration of the drug in that patient's drip bag becomes very important. Now the key thing to remember is that if you take a specific volume of a more concentrated solution and add more solvent to it to dilute it, the number of moles of the solute does not change. So the chemical is not being created or destroyed by this means. And because of this, if you increase the volume of a solution by adding solvent, you are therefore decreasing the concentration. These relationships are shown in this equation. C1 times V1 is equal to C2 times V2. Now the terms on the left hand side represent the concentration and volume of your starting solution. Those on the right hand side are for your resulting solution. So you can see that because the left hand side is equal to the right hand side, if you increase the volume on the right, you must decrease the concentration on the right. Now in example calculations, you're always going to be given 3 out of these 4 terms. So with some very simple manipulation of the equation, you can work out the missing term. Here's a practice problem. So you have a stock solution of potassium permanganate with a concentration of 0.25 moles per litre. You need to make 200 millilitres of more dilute 0.005 moles per litre permanganate solution. So what volume of stock solution do you use? You can pause the video now and have a go at working this out if you feel confident enough. So looking at the equation, it's all about identifying the terms with the information that you're given. We know what our 2 terms are for the right hand side of the equation because we're told that the resulting solution should be 0.005 moles per litre and 200 millilitres. So we know C2 and V2. We're also told that our stock solution is 0.25 moles per litre, so we also know C1. Our missing term is V1. To get this term on its own, all we need to do is divide both sides of the equation by C1, and then of course cancels out on the left hand side. So now it's quite simple. Our calculation is just 0.005 times 200 all over 0.25, and that gives us, it comes out as 4 millilitres of the stock solution. Nice thing about this equation is that you can use whatever units you like for the concentrations and volumes. They don't have to be molarities, although they were in the example we just saw. As long as the units for concentrations and for volumes match on both sides of the equation, it's good to use. So for example, the units in this version of the equation would be absolutely fine to use. However, the units in this version would not be okay to use as given. You would have to convert millimolar to molar, or vice versa, to make the equation work for you. There are lots of questions on the accompanying worksheet, as I've said, to have a go at. They start simple and get a bit more complex. Doing calculations with moles and concentrations is a skill that is developed over time and needs to be worked at over a long time frame. But this, more than perhaps anything else, is really an aspect of chemistry that you will apply and use in a multitude of scientific disciplines and roles. So I'll leave you with a reminder of the learning objectives. Thank you for watching the video and good luck.